Okay, so thank you everyone. Welcome. Good morning or good afternoon if you are watching from some other place. This is the great things of these online conferences that we could reach a lot of different people from different places. In this session, I wanted to give you an overview and a walkthrough of how we could use one of the most powerful constructors and concurrency so that we could allow our users or the developers that are going to use some library that we are working or some platform that we are creating to get the most of the concurrency mechanism that Java have in the platform, and to get the most of our library and the way that we offer our API. So let's briefly start by defining a couple of concepts and to take a very brief overview of what concurrency and parallelism was in Java from the very beginning. And I will very quickly go straight to the point and see what CompletableFutures had to offer, but we need to put them a little bit into context and see what the path was until we are where we are right now with Java. So the first thing that I would like to define is concurrency and parallelism. Basically, parallelism, probably we are more used to that. And parallelism means that we have a workload, and this workload is composed of a lot of small tasks, or we could divide that workload into a smaller tasks. But basically, those tasks are always the same and are homogeneous, and they will be worked the same way. So one of the things that we could do is basically try to split this workload between a number of workers or a number of threads and put all of them to work in parallel, doing basically or executing the same code that is going to render the final results. Basically, our goal with this is to try to have all our potential in our CPU or our cores, CPU cores, to work and get out the most of our machine power. On the other side, concurrency is more or less the kind of strategy that we use when we have different types of tasks. And in this case, what we are going to do is basically try to take the most of the time when we are waiting for some task to finish or to some external system to do their work. We are going to try to use that time, that waiting time, to do something else that will be useful later. This is more or less similar to, for example, if you are cooking a recipe in your kitchen, probably there are some steps in which you need to wait. For example, you at some point reading your recipe, you will have to wait. You will put something in the oven and you will have to wait, I don't know, 30, 40 minutes until the food is cooked. But in the meantime, instead of waiting, sitting there and wait until the oven is finished, you could start preparing some sauce or something else that you are going to add to the final dish. So this is more or less concurrency. Concurrency means instead of waiting until something happens or some task is finished, try to use that time to do something else that will be useful afterwards. Again, in the same way that parallelism is some strategy that we use to get the whole workload done as soon as possible. Concurrency is exactly the same. Our goal is to have the work finished as soon as possible. But in this time, we are dealing with different kind of tasks, and probably we are dealing with tasks that don't entirely depend on us. Maybe we are going to ask some external system, and that external system is going to take some time to answer and to give the results. So we want to have something that allow us to run some other code while we are waiting. In Java, we have support for concurrency and parallelism since the very beginning in the form of threads. And these initial versions of Java had a very basic support for concurrency and parallelism. And even when most desktop computers were single core, we could benefit from that. The way we used to do that was by using thread. And probably most of you have already at some point in your career written this kind of code in which we basically had to create a new thread and then start the thread and then wait for the thread to finish its work. The problem with this kind of approach is that first, creating new threads is a very expensive operation. We have always said that creating new objects in Java is one of the most expensive operations in terms of time. But specifically creating a new thread means that we need to also synchronize with the operating system to create a new process at the operating system level. But also usually, and this is something that I even had done, I have forgotten sometimes to start the thread. And finally, when we want to wait for the thread to finish, we will just join for the thread. And that means that we are going to sit waiting on our main thread. So basically, the first approach to solve this problem was in the very beginning to create thread pools. Thread pools were usually created by developers on ourselves. And basically, that means that we had some kind of container for a group of threads that will be started from the very beginning and will never be ended until the thread pool is shut down. And we had this queue in which a client thread could submit new tasks, and these tasks will be added to the queue so that the worker threads could get notified and retrieve those tasks and start working on those tasks while that were submitted by the client threads. So this is basically the way that we could use the threads to create something that will allow to run things concurrently. But it was kind of a very manual thing to do, and it took time, and we had to design our thread pools very carefully. But since Java 5, we had also a very big improvement in how Java was supporting concurrency. There's a very good book on that, Java Concurrency in Practice, which basically summarizes all the changes and all the new constructors, new concurrency constructors that were added since Java 5. Not only new constructors, synchronizers, there were some data structures that were designed specifically to better support concurrency and parallelism. And even after that version in Java 7 and Java 8 and Java 9, every single version has tried to redo and improve all these constructors and concurrency supports that we have in Java. In fact, in the recent versions of Java, or since a couple of years, there were a new project, which is the Loom project, which is basically focused on adding new ways of improving even more the way that we can use concurrency and threads in Java. But let's see how we could run tasks asynchronously in a better way since Java 5. The first thing that we have is the executor service. The executor service basically was added in Java 5, and it's basically a proper implementation of thread pool, but this is really available on Java out of the box. And basically the main thing that we have is that instead of just running runnables, instead of just running tasks that return no result, we now can also submit some different type of tasks that are called callables. Callables basically is a similar interface to runnable, in which the method, which is not just run something and returns void, callables will run something and returns some kind of results of type R in this case. So when the executor service gets, or when we submit a new callable to the executor service, the thing that we will have in return is something called a future of R. A future of R basically is a container that will give us a pointer to the task that has been submitted to the executor service. That means that we can wait and get the information, the results, whenever it's ready, or we could even cancel that task that we have asked to run asynchronously. How we use this future, basically, the first thing that we need to do is create the executor service. For that, we have a class, an executors class, that provides a set of factory methods that will allow us to get some default implementations of the executor service. The good thing from the executor service is that we can customize several things, like, for example, the size of the executor service, the implementation of the queue that we are going to use for that thread pool, or the policy, the factory that is going to be used to create new threads, or which is the rejection policy that we are going to get whenever, or the rejection policy that is going to be executed whenever we submit a new task and the executor service can't execute that because it's full, the queue is full, or it has no idle work threads, or the executor service has been instructed to shut down, to finish its work. So the rejection policy means that we also can customize the way that the executor service is going to reject all the tasks that we have submitted that executor service can't execute. So once that we have this executor service, the next thing that we need to do is to submit our long-running task. This is similar to what we had with the runnable. This is basically a runnable that we are going to submit, and we are asked the executor service, the thread pool, to execute whenever it's ready. Basically, after that, we will get that future, and that future, it's, as I was saying before, a pointer to the task that we have submitted. So we can ask the future to get its value. The thing is that this .get method is a blocking call. It's the same thing that we had with thread.join, and our main thread, our client thread, the thread that has asked it to execute that asynchronously, is going to sit and wait until the other thread, the executor service, has finished its work. So maybe this is not what we want to have, but with the future, one of the things that we could do is we could enter a loop in which what we could do is we could ask the future whether it's done, whether the task is finished or not. And while the task is not finished, we could go do something else. We could go and try to execute some other code that will be useful while the main task is still executing. So once that the task result is done, returns true, we know that we could get the value. So this is a very useful way to improve the performance by doing something, by trying to do something while the food is cooking in the oven. But we have, if we have multiple tasks, what we could do is basically we could add all of them as runnables to the executor service. In this case, we could enter a loop and submit all those tasks. And whenever all those tasks are submitted, we can start retrieving the information. So this is a little bit better, but the problem here is that we only are benefiting from the time that we take for submitting the task. And this is usually very quick. So in this case, we are going to submit all our tasks to the executor service, and then we will start waiting for the task to be returned. But usually, when we are speaking about heterogeneous tasks, when we are not speaking about CPU-intensive tasks, when we are speaking about tasks that they are going to query an external system that may take some time to respond, the thing is that we don't know for sure how much time that task is going to take to finish. And we could face a problem that if we are querying different systems, different external systems, some of them or some of those queries could be really fast, really quick, and some other will be too slow. So with this code, the problem that we have is that if the first task is going to take a lot of time and the second task is very quick, we will be sitting, because we are iterating over the futures in the same order that we submitted them to the executor service. We are going to sit and wait until the first task has finished, while maybe the second task is already finished and we could be processing its result. And still we are waiting for the first task to finish. So there's another interface, which is completion service, that could help us in this case, because completion service, basically what it does is it basically wraps the executor service and it returns the tasks not in the order that they were submitted, but in the order that they are finished. So this is an improvement over the executor service that allows us to start processing tasks as they are ready, not in the same order that we submitted them. But there's another problem in this case. What if the kind of tasks that we have in our system are dependent or are interdependent between them? What if, in order to submit the second task, we need some value calculated by the first task to be provided? So that would mean that we need to run the task one and wait until task one is executed in order to be able to submit the second task to the executor service. And in the meantime, maybe we could be even processing some other external tasks. So this is kind of a more complex scenario, but it's usual that we could face this kind of situations. So this is where the main purpose of this talk comes up. This is why the completable future was added in Java 8 also. So let's see how completable future helps us to deal with that. Completable future was added in Java 8 also, and the main thing is that it's going to take a different approach on how we are going to submit new asynchronous tasks to be run on that executor service. Completable future, instead of using the executor service to submit this task, completable future has factory method, has static methods to submit new tasks to an executor service. And more important is that it also implements a Fluent API that allows us to combine, compose, and chain these different tasks when they depend on each other. So that's basically what the main purpose of completable future is. But also, it allows us to use different executor service configured in different ways, depending on the kind of tasks that we are executing. So even in the case that we have heterogeneous tasks that are going to do different things, maybe we have a first task that is going to query something from an external system that is going to take some time, and then we will probably have another second task that is going to process that request that is CPU intensive, and we could use a different size executor service or a different size thread pool. So this is something very useful also in the way that we use completable futures. Let's see this with an example. The first thing that we need to do in order to submit a task using a completable future is we need to use the run async method. This is the very same runnable, the very same long running task that returns no results that we want to be executed using completable futures. So what we do is completable future.run async, and we provide our runnable there, and that runnable will return no result. So our completable future will be a completable future void. That means that there's no point in trying to get a result from this task because it returns no result. But the thing that we could do is we could try to cancel that task or ask whether that task is already finished or not. And in the meantime, while this task is running asynchronously, we could be doing something else. And finally, we could at some point get, again, we are not going to retrieve the result because that task returns no result, but we are going to make sure that this CompletableFuture has, or this task has finished before going on. So if we use this method, this runAsync method, we are not providing any information on which executor service should be used for that. And this means that we are going to use the default strategy. And the default strategy is either we are going to use the common for join pool, which is something that was added in Java 7, or in the worst case scenario, we are going to use a thread per task executor. This is only when the common for join pool has a size of just one thread. If the common for join pool in our machine only has one thread, the default strategy that the CompletableFutures is going to use for the executor service is just the new thread per task executor. Let's see how these two strategies works. Basically, the common for join pool is a pool that is shared with the rest of the JVM. So using this pool for submitting our asynchronous tasks that may be asking some external system may indeed be affecting some other parts of our code, particularly the parallel streams on Java 8 are using the common for join pool. So we may be impacting the performance of any other place in which we are using parallel streams in our application. And this is because also the common for join pool is usually sized to get the most of our system, considering that the kind of tasks that we are submitting to be run in the common for join pool are CPU intensive. That means that if we are going to make our common thread or our worker thread sit and wait until some network call has finished, we will be delaying any other task that was submitted to the common for join pool because there are no more threads available. And finally, another property that the common for join pool threads have is that they are daemon threads. And that means that if a daemon thread means that if there are no other threads in the system running, the daemon thread is not taken into account in order to finish the JVM. So that means basically that we may end up with our common for join pool being shut down while our task hasn't been executed because at some point the application stopped. On the other side, using if our common for join pool has the size of 1, the default strategies will be thread per task executor, which is basically the very same that we saw on our first slide. We already knew that this is not a very good idea in terms of performance because it's very expensive to create a new thread for each task. So basically, that's what we have when we use the runAsync method. The way we could improve that is first we could create our own executor service. And once that we have our executor service, the thing that we need to do is basically use another overloaded method that allows us to specify the executor service that we are going to use for running that particular task. So in this case, we could be providing a better executor service, which is sized accordingly to the kind of percentage of time that we expect our task to be waiting for the network call or for retrieving some information. So this is basically when we have tasks that return no result. But what if we have some task that returns a certain result and we're interested in that? In this case, our task won't be a runnable, will be a callable, will be a long-running task that result. And in this case, we cannot use the run async method. The method that we need to use is we need to remove the run async and use the supply async method. Supply async method means that it's going to wait for a callable, and accordingly, that callable will return something that will be the result of our completable future. So in this case, our completable future, our result.get will return whenever it's ready the string that came out as a result of our task. So this is basically the way that we use CompletableFutures to run something asynchronously. But so far, you may be thinking that it's just a different way of submitting asynchronous tasks to be run. But the thing is that the CompletableFuture is not just a future. It also implements another interface, which is completion states. And the completion states is where the interesting bits of CompletableFuture comes, because completion states is an interface that defines a Fluent API that allows us to chain different tasks. In this scenario in which we have different tasks that depend on each other, we could combine, compose, and chain those so that, for example, we could split different tasks and wait until all of them have been finished, or we could set up that whenever one task is finished, we will provide, using, for example, then accept or then combine, another handler, another method, another task that is going to be called after the first task is finished automatically. And sometimes, depending on the method that we are going to use, it will provide the result of the first task as the entry point to the second task. So once that we are using CompletableFutures, the main thing that we should do is we should try to find exploitable concurrency in our code. Usually, this is very important to take a look into what are the EO-bound tasks. What are the tasks that are going to wait potentially for some network call to finish or for an external system to reply? And if we are able to try to draw the diagram of these different tasks and how they relate to each other, it's a better way that we could have a good understanding on how we are going to combine and compose the different completable futures. So let's try to see a quick example of this. This is a lot of code, but we are going to go through it step by step. Let's say that we have an online store, and this online store has, of course, a checkout process. Whenever we receive a checkout command, a request that is asking to our system to process a shopping cart and to make and schedule the deliveries, the first thing that we need to do, for example, could be to retrieve the shopping cart itself, because probably on the command request, on the request to process the shopping cart, we are not going to receive all the information about the shopping cart. What makes sense is that the command is going to get only the required information for us to know what we should be doing. And in this case, we are going to be provided by the shopping cart ID. So the first thing we need to do is ask some kind of shopping cart service and find the cart that will return the shopping cart with all the product items. The next thing that we are going to do is we are going to iterate over the different elements, the different items in our shopping cart, because let's say that our online store is more like a mall, is dealing with different warehouses and different shops. And we need to go over the different products and ask the different warehouses for the product availability, because sometimes we may have availability immediately, and sometimes we may have availability in a couple of days. So we are going to retrieve all the product availabilities for the different products. But one of the things that we want for our store is we don't want the customer to wait until the moment that the last product is available in order to receive their packets. The thing that we want to do is we want our customer to receive their products as soon as they are ready. So what we are going to do also is once that we have all those deliveries, we are going to group those deliveries by availability date, and we are going to start sending those packages as soon as they are ready. Finally, and in parallel, maybe we are working with a courier company that depends, for example, on the price depends, for example, on things like where the customer lives, or it depends, the price that we are going to get charged depends on how much volume, how much business we are doing with them, and it may depend from time to time the different price. So we also need to ask our courier company for the quote, for the price, for sending some deliveries that we are going to schedule immediately. And finally, with that information and the amount of deliveries that we have, we probably need to calculate the shipping cost. So basically, this is the process of the code, but this is in a diagram. It could be look something like this. We are going to get the shopping cart, then we are going to iterate, asking external inventory systems for the product availability, and this may take some time to fill. So after that, after we have iterated over all the products, we will group the deliveries, and then we will get the courier quote, and then we will calculate the shipping cost. So this is going to take a while because we are iterating and we are relying on external systems that we don't know how much time they will get. So a first way in which we could improve that is by, for example, trying to get the courier code in parallel. So we will create two tasks, one to get all the information about the deliveries, and the other one to, in parallel, try to retrieve the cost of the delivery. But we could even improve a little bit more, because on the right side of our diagram, we could split in parallel and ask the different warehouses about the product availability. And then as they are ready, we could try to merge them and group into the deliveries. So that will probably be more performant because we are trying to take the most of the time, and we are trying to send in parallel all the requests to the different warehouses. So if we were to write this using regular threads, it could be really complicated. If we use CompletableFutures, basically what we could do, this is just the part of splitting the different queries to the warehouses. Where we could do is first, we need to supply an asynchronous task, which is basically getting the find card by ID. This will return a card. So after that, we are going to combine and to specify a chain in which we are going to add a second task, which is basically dependent on the first one. So the second task that is linked with the then asset assigned will receive the result of the first task. And this is a card. On the card, we are going to get a stream with the different items. And for each of these items, we are going to create a new task, a new completable future that is going to retrieve the availability from the inventory service. Then once that any of these individual tasks are completed, we are going to chain a second task, which is going to group the delivery, that specific delivery, with the rest of the already available done. So finally, we are going to collect, and this will get a list of completable futures, and we are going to make sure that all these futures have finished until we can go on. So this is more or less a way to implement and chain all the different steps that we have there. So this is how we use CompletableFutures, but what I wanted to point out in this talk is how you could, if you are writing a library, why you should be considering to use CompletableFutures as a return type from your methods. For example, this is one of the things that allows your platform or your library to make more performant. So the way that we do this is basically you need to, in order to provide a completable feature, you need to create a new completable feature that will give us a box that will contain a result that will be able, that we could return to the client, and the client will get that information that we have seen in order to chain different tasks or to ask for the result or ask if it's done or if has executed with some kind of problem. But on the other side, for us, the writers of this library allows us to provide, when the task has been completed, the result of that, or to specify that we have seen some kind of error and complete exceptionally, marking it as an error. Let's go focus on this second part, and let's try to see how we are using that on Action Framework. And very briefly, I will introduce Action Framework in order to you to know what we are doing. Action Framework basically is an open source framework that allows you to write applications following CQRS. That means splitting queries and commands in different modules, and also using JDD to model your different areas, the command model and the query model. And it also coordinates all the modules using event sourcing, which means that we will not only provide events to coordinate those, but all the events will be the source of truth to reveal at any point in time the status of any entity. If you are interested into this concretely, I will give some pointers to you at the final slide of this talk. But let's focus on how we have implemented the query API for our model. Basically, what we have is we have a query bus, which is going to receive all the query messages. Whenever a user wants to make a query to our system, he's going to put a query message into the query bus, and this query message will be delivered by the Action Framework to the right module that is going to handle that query and provide the results. But one of the things that we wanted to do is to allow the developer that is going to create or to use our API to specify if they have to run different queries, so that they will have the option to make more powerful use and get the better performance from our API. So this is a very simplified version of what the implementation of our query method is, but you could look at it because our framework is open source. So basically what we receive is a query message, and the query message on the query bus, basically the first thing that it need to do is create a completable feature that will return a query response message. And we are going to return as soon as we can that query transaction, even if we don't have already the results of that, because we are going to run asynchronously the query. So the next thing that we need to do is we need to prepare to run asynchronously our solution. So in this case, in case that we have any kind of exception, we will just mark the query transaction completed with an exception. And finally, we could get the connection. This is where the asynchronous part is coming. We will get the connection and query the connection. Our Action Server Connection Manager is already implementing some kind of asynchronous work. So the result that is going to retrieve will give us a callable when the data is available. And in that callable, we are going to mark the transaction as complete, so that we are in fact returning the query transaction, the completable future, even before we have run the query against the server. So that means that our users will be able to get the most of our queries. They will be able to compose this. I'm going to finish with a couple of final thoughts. The first thing is when we are running CompletableFutures, we need to make sure that in the implementation of our library, we are taking care of running this in asynchronous mode. Indeed, we have a simple implementation of our query boost that is not async, it's just serial, but for demo purposes or for local environments is very useful. Also, you need to take into account which executor service you are using. Try to avoid using the default common for joy pool or the default policy. And finally, keep in mind that CompletableFutures are really powerful for composing and combining, but sometimes it's hard to get it right. So your users should be able to understand completely how CompletableFutures works. Final conclusions. CompletableFutures are a powerful tool to compose and combine the execution of asynchronous tasks. And if the executor service, it's better to provide your own executor service that is properly sizes based on the kind of task that you're executing, and try to use your CompletableFutures and your API if you want to make a really powerful library. So if you're interested in going into more detail, I will leave you here. You can find a page with I have get all the resources that I'm going to talk about. There's a very good blog post by Maurice Naftalin talking about how to use CompletableFutures. There's also a very good resource, the Java Specialist newsletter. If you don't know that, try to subscribe, because there's lots of interesting posts on Java concurrency and Java performance. Also, there are some advanced Java concurrency courses available there. Of course, the Java concurrency in practice book is still up to date. And if you want to know a little bit more about Action Framework, it's an open source framework. You can go yourself and see the implementation and that repository. You also have a quick start tutorial if you want to get started on how Action Framework works. And finally, we have an Action Academy with free courses on JDD, CQRS, and how could you use event sourcing to build modular monoliths that could scale to microservices when you are ready to. So that's all the hints that I have. And again, go to that landing page, scan that QR code, and you will get all the information that I'm having here. And with that, we can go back to the studio. And if you have any questions, I will be glad to answer them.